And today we have Professor Victor Torres-Company from Chalmers and Pascual Muñoz from UPV. And the first speaker is Victor, and title of his talk is Dark Solitons in Optical Microresonators. Yes, Victor, please, welcome.
Thank you, Dmitry. So let me see if I can share the screen. So I changed slightly the title. I hope that's fine. I'm calling now Dark Pulse Kercombs in Silicon Nitride Microresonators. So I just would like to start by thanking Dmitry and Joanna for organizing this webinar series in the framework of the Microcomb ITN. It's really a great pleasure and an honor to be part of this consortium, and I am very much looking forward to meeting you all in person and hopefully in a not very distant future. So my name is Victor Torres, and I am an associate professor at Chalmers University of Technology. I'm responsible for a small team of researchers that come from many different places around the world. So these are really the key people who work very hard in the lab and the ones who are really at the front line of the research. And my team, we work on different areas, from nanofabrication of microresonators to modeling and characterization, up to system-level validation of our devices in the context of high-speed optical communication systems. And by the way, we have a couple of postdoc openings in my group, so if you are interested, please don't hesitate to drop me an email. So we are also very privileged to count with a number of collaborations in the field of microcombs and related technologies from Chalmers, DTU, Purdue, Ghent, and UPV with Pascual Muñoz. I think most relevant for the talk that I'm going to give now is the collaboration with Purdue, with Andy Weiner, and with Peter Andreksson at Chalmers. Okay, so I was just saying that given that this webinar series is aimed at instructing some PhD students that just started, I decided to spend a little bit of extra time in covering some background related to microcombs and frequency combs. So then I'll spend a few words to cover silicon nitride, but I'll leave the main course, so to say, to Pascual. And then I will introduce dark pulse Kercombs, which I think are really fascinating solitary waves that lead to coherent microcombs that have very interesting properties, but in my opinion, do not get all the attention that they deserve. And then in the end, I will highlight a couple of relevant examples of microcombs in the field of coherent optical communications. So I think it's instructive to contextualize the field of microcombs by giving a little bit of historical perspective. Before laser frequency combs were developed, laser spectroscopists and atomic physics experimentalists were faced with the following challenge. So imagine that you wanted to measure the frequency of a laser that interacts with an atom or a molecule system. So if you want to do this measurement with absolute accuracy, you must refer the optical frequency to an SI standard. So today, the standard of frequency is given by a hyperfine transition in cesium, which is very close to 10 gigahertz. So if you really want to measure your optical frequency, then you need to compare its value to 10 gigahertz. So this means, in other words, that you need to compare two frequencies that differ between them by 4 orders of magnitude. So I like to make this analogy that it is like measuring a soccer field, but with a super accurate ruler, but that this ruler is just 1 centimeter long. So if you're acquainted with microwave hardware, you may be tempted to think that you could do this, but with just a 10,000 multiplier, right? Well, believe it or not, this is how people approach the problem for laser frequency combs were invented. So these multipliers are called harmonic frequency chains, and they occupy an entire research facility. As a result, only very few laboratories in the world could do this sort of precision measurements. Harmonic frequency chains had also an additional drawback, which is that they had to be specifically designed for one particular optical frequency. If all of a sudden you want to measure a different optical frequency, then you had to rebuild completely, almost from scratch, your harmonic frequency chain. So the idea of using frequency combs was put forward much earlier, and like many other great ideas, it is conceptually simple. So the idea is to use a monologue laser as a frequency ruler against which to compare your unknown optical frequency. So the idea is that your monologue laser emits a series of ultra-short optical pulses that are coming in a repetitive fashion. So the optical spectrum of this monologue laser corresponds to a series of evenly spaced frequency lines where the frequency spacing between two consecutive lines is exactly given by the repetition rate of the pulse train. And the shorter the pulses, the broader the spectrum. So you have many more lines, essentially. So the idea of using this comb of frequencies for measuring an unknown optical frequency is to beat your unknown continuous wave laser against the monologue laser. And after measuring this bit node, then you know essentially how far in frequency you are with respect to the closest mode of the monologue laser. Then in principle, you could infer the color or the frequency of your laser. Well, the idea was developed in the late 70s, right? And people still in the 90s prefer to develop these complex harmonic frequency chains. So you know that there is a flaw and there's a catch here. But where is the flaw? The flaw is in the assumption that you know exactly which comb line you are beating your laser with. So if you take a closer look to the spectrum of the pulse train, you realize that the carrier frequency is not necessarily a multiple integer of the repetition rate of the pulse train. As a result, the comb of frequencies appears slightly shifted by a non-zero quantity with respect to absolute zero. So you know that each mode in the comb is exactly a multiple integer of your repetition rate plus this small frequency offset. So the thing is that while the repetition rate can be measured and even stabilized, it was not possible in the late 90s to measure and stabilize the offset frequency. Therefore, there was an ambiguity in labeling the frequency lines of the spectrum of a monologue laser. So the possibility for measuring the offset in a monologue laser came with the development of the photonic crystal fibers. I don't want to enter into much technical details, but this fiber enabled the development of a technique that is called self-referencing. And the thing with this technique is that one can measure the offset frequency of a monologue laser by beating the low frequency side of the spectrum that comes out of this photonic crystal fiber with the high frequency side of the spectrum. So by measuring the offset frequency of the monologue laser, at the end of the day allows for the synthesis and the control of the 2 degrees of freedom of your monologue laser spectrum. And this was a huge revolution in laser science that culminated in the Nobel Prize in Physics awarded in 2005 to professors Ted Hans and John Hall. And today one can actually buy these frequency combs based on monologue lasers, for instance, from our colleagues at Menlo, but there are other companies around the world, for example, Toptica in Munich as well, or INRA in the US, that are also selling these systems. So laser frequency combs based on monologue lasers allow for a huge simplification for the systems that were used to measure optical frequencies with absolute accuracy. So to a large extent, today, microresonator frequency combs are holding the promise for the next leap forward in this field by achieving the same sort of level of accuracy, but using chip-scale photonic integration. And that's exactly the topic of my talk and the topic and the training in this ITN. So microresonator frequency combs were pioneered more than a decade ago today by our colleagues Tobias Kippenberg and Pascal Delhaye, who are members also in this ITN network. So similar to monologue lasers, they provide a ruler of optical frequencies that forms the core of a frequency comb. So microresonator frequency combs essentially leverage the nonlinear Kerr effect in a high Q optical cavity. So when a continuous wave laser is tuned into one of the longitudinal modes of the cavity, the intensity builds up and nonlinear phenomena can be harnessed at very low powers. So the comb of optical frequencies can be generated by a cascade of 4-wave mixing that populates the longitudinal modes of the cavity. The really cool thing about this microcavity is that it can be fabricated in integrated platforms. such that the free spectral range and therefore the comb line spacing can be much, much larger than what can be obtained with just standard passively modeled lasers. In addition, here there is no optical amplification by stimulated emission of radiation, and the bandwidth instead is just given by the dispersion in the cavity. And with fabrication techniques and novel material platforms, this can be engineered to cover more than one octave. So overall, at the end of the day, this is a very simple, all optical, nonlinear process where a laser pump just coupled to one microcavity can generate the comb of evenly spaced optical frequencies. So it's really this unique combination of large comb line spacing and the possibility to attain photonic integration that is enabling a whole new range of possibilities that go from the calibration of astronomical spectrographs all the way up to the synthesis and control of optical frequencies and coherent optical communications. So it's quite interesting that the dynamics that lead to the formation of microcombs are quite universal. And you can find the same sort of microcomb spectra in completely different material platforms and techniques. For example, the first demonstrations were developed in crystalline whispering gallery mode resonators and microtoroid that display extremely high Q factor, but have a relatively low nonlinear coefficient and relatively low linear refractive index. Later on, it was recognized that other planar microresonators based on amorphous dielectrics could, as well as semiconductors, could also be used to generate Kerr frequency combs. These materials essentially have higher linear refractive index and therefore are more susceptible to scattering losses, which results in a lower Q factor compared to crystalline whispering gallery mode resonators. However, this is offset by having a slightly higher nonlinear Kerr coefficient. In addition, some semiconductors, as well as ferroelectrics, have other very interesting properties, such as a non-vanishing second-order nonlinearity or a relatively high electro-optic coefficient, which can be used to, generate new devices on chip or to provide enhanced functionality to microcombs. So just taking a closer look at silicon nitride, this is just an amorphous dielectric material that is compatible with CMOS fabrication standards. It has a moderate nonlinear Kerr coefficient that is just 10 times higher than silica and moderate linear refractive index, but sufficiently high such that it allows a strong optical field confinement when you have silica as the cladding material. In addition, it has a very large ultra-broad transparency window that covers from the UV/blue light all the way up to the mid-infrared. So if you can really control the dispersion inside this window, then you can generate combs over a very broad spectral window. And this is really why many groups in the world are working in this material platform for microcomb generation. At Chalmers, we have developed a subtractive processing method to fabricate low loss, high confinement, dispersion engineer silicon nitride waveguides. And you may think that, since there are so many groups in the world working on silicon nitride, that this is a very established and rudimentary fabrication process, but this is very far from the reality. So what you see in this slide is the process flow in our technology. So we start with an oxidized 3 or nowadays 4-inch silicon wafer. So after oxidations, we create a set of crack barriers with laser lithography. The reason for this step is that it's important to manage the formation of cracks in the subsequent silicon nitride layer, because they are generated typically from the outer side of the wafer. Then we deposit a silicon nitride film with the desired thickness, but we do it in 2 steps, with a high temperature annealing step in between. Then we pattern the silicon nitride layer and clad the structures with silicon. The thing is that every single step in this process was optimized for several months, sometimes for years, in order to achieve waveguides with very, very smooth sidewalls, because sidewall roughness appeared to be the dominant loss contribution that limited the Q factor in our silicon nitride and microresonators. So the end result is a dispersion engineered and reproducible silicon nitride platform that results in a mean Q that exceeds 10 million. So I'm not going to claim that this is the world record Q in silicon nitride, but what I can tell is that very few groups in the world can reach this performance level, and we're certainly very proud of this. So besides microresonators, we have other low-loss interfaces with fiber lasers. We have also developed high-speed thermo-optic shifters and an extensive library of devices and components such as AWGs, Mach-Zehnder interferometers, MMIs, etc. We have also recently developed a low-loss platform in 1 micron, but this is just for linear optics applications, concretely for optical interconnects based on Bexel technology. We've done this also in collaboration with Anders Larsson at Chalmers and also with Pascual Muñoz at UPV. So regarding microcomb generation, I think it's quite interesting to see that completely different results can be obtained depending on how do you actually engineer your cross-section geometry in the waveguide. So in the upper figure, what you see is a coherent comb with a comb line spacing around 200 gigahertz, with some structure in the comb envelope, but with very, very high conversion efficiency. With conversion efficiency, I mean the amount of comb power that you get, excluding the pump, divided by amount of input power that you send into your device. So if one now changes slightly the cross-section geometry by making it slightly thicker but narrower, then you can generate a very broad microcomb that corresponds in the time domain to a circulating soliton in the cavity. In this case, as you can see, the envelope is very, very smooth, but the conversion efficiency drops to below 1%. Both of these combs correspond in the time domain to stationary waveforms, but completely different to each other, that are circulating in the cavity at a rate that is commensurate to the free spectral range. And they both lead to very coherent and stable microcombs. So the reason for this apparent different dynamics lies in the dispersion of the fundamental mode in the cavity is completely different in either case. So in the case of the temporal soliton, the cavity displays anomalous dispersion. This means that the blue components for that particular mode travel faster than the red ones, and that leads to an FSR that increases with higher frequencies. In the case of the structured waveforms, what happens is that the dispersion of the fundamental mode is designed to operate in the normal dispersion regime, meaning that just the opposite, that blue frequency components travel slower than the red ones, and that leads to a free spectral range that decreases with increasing frequencies. So this normal dispersion regime has been less investigated in the literature, but it's actually quite interesting, because these combs actually lead to much higher power conversion efficiency. The intracavity waveform here does not correspond to a very well-defined pulse, but instead what it seems to appear is a deep or a hole of light that sits from a high-intensity background. So the emergence of this type of frequency comb can actually be understood by analyzing the power stability diagram in the cavity. So the time domain waveform can be understood as if you had two interlocked switching waves that connect the two homogeneous steady state power levels in the cavity. The thing is that while this picture accounts for most of the most salient and relevant characteristics of this type of frequency combs, it actually fails at accounting for the dynamics of the comb formation starting from a continuous wave laser. If you want to understand how this type of combs are generated starting from a continuous wave laser, you need to acknowledge that this sort of cavity actually sustains more than one mode, more than one transverse mode. So these two transverse modes that appear in the cavity appear linearly coupled to each other because, for example, some random effect in the fabrication process that breaks the orthogonality of the modes. So the formation of these dark pulse Kerr combs takes place when a laser is tuned from the blue side into a pair of linearly coupled longitudinal modes, or so-called hybrid modes in the supermode picture. So I think this is going to be better understood in this video. Let's hope it works. So what you see here before the video starts is a pair of hybridized resonances. These are actual measurements. And the solid red line corresponds to the location of the continuous wave laser. This is on the left-hand side, and on the right-hand side, what you see is a recording of the optical spectra as we tune in the laser into the resonances. So let's see the video. So let's see. So you see that as the laser goes into the resonance, it pushes the two set of resonances to the red, and you see that nothing really happens in the optical spectrum until the laser crosses the first resonance, and then all of a sudden the dark pulse Kerr-Comb emerges. And if you look carefully, you will see that there has appeared an extra resonance in between. Okay, and if you keep continuing to, if you keep continuing, you generate the comb, they keep continuing, then what happens is that the laser crosses the second resonance, and the two hybridized resonances cool down and come back to the original state. So the appearance of this extra resonance can be understood based on the structure of the time domain waveform, this dark pulse that is circulating inside the cavity. So when the dark pulse is formed inside, these two power levels will introduce two different Kerr nonlinear phase shifts into the cavity resonance, causing what appears to be a split resonance from the perspective of the continuous wave laser. So similar observations have been made for cavity solitons in the anomalous dispersion regime. So the appearance of these extra resonances are a signature that the comb is in a moduloc state, and that the cavity is and that the waveform breaks the time invariance of the system. But the cool thing is that, unlike with the cavity solitons, with moduloc Kerr-Combs operating the normal dispersion regime, these extra resonances, the extra resonance appears to the blue side of the pump, and it does correspond to the dark or lower power part of the waveform. The high power part appears to the red side, but this is the CW power that corresponds to the upper branch in the stability core. So the high and lower power levels shift the resonances in the same way as with the solitons in the anomalous dispersion regime, but in the dark pulse Kerr-Combs, the high power level corresponds to the CW background. So as a result, the CW laser appears effectively blue detuned with respect to the pump resonance. And this is important because it facilitates a thermal lock-in between the laser and the microresonator. So another interesting characteristics of these dark pulse Kerr-Combs is that in the path towards the formation, different states can be accessed in a sequential and reversible manner. So each state does correspond to a distinct waveform that is characterized by an integer number of oscillations at the bottom of the waveform. So by controlling the detuning, one can access a single dark pulse Kerr-Comb that resembles very much a gray soliton in the nonlinear Schrödinger picture. However, strictly speaking, this is not a gray soliton, because if you analyze the phase, you realize that this is not an odd function, as it should be, because the phase should be an even function such that it allows for stitching together multiple waveforms that are repetitive in the resonator. So the problem with these dark pulse Kerr-Combs is that they exist only in microresonators that display sufficient amount of coupling strength between the two transverse modes. Okay, so this has been based on all these previous experiments. The problem is that you don't really have a handle on how to control this amount of coupling between the two transverse modes. And the result is that one can get dark pulse Kerr-Combs only in resonators that one has measured and characterized a posteriori. So one solution to this problem is to engineer the coupling by making use of an arrangement of linearly coupled cavities. Okay, and this sort of geometry can be understood as a photonic diatomic molecule, where the cavities represent artificial atoms with the longitudinal modes being the atomic energy levels. So the interesting bit is that the coupling modifies the energy spectrum by creating a coherent superposition of the wave functions of the atoms. And that results in a completely different energy spectrum, a completely different set of resonant modes. So this sort of arrangement has been studied before by colleagues at Purdue and also at Columbia, and they discovered that this system can actually provide coherent microcombs with very high conversion efficiency. So we have studied this system using our silicon nitride technology and discovered that this coupling changes dramatically the landscape of existence for dark pulse Kercombs. So what you see in the left panel is the existence range for a fixed coupling coefficient and different pump power levels and different detuning levels. So the brown shadow area corresponds to the existence range of dark pulse Kercombs when you only use a single cavity arrangement. And the blue shadow area, that corresponds to the existence range in the case where the two cavities are linearly coupled. So you see that this cavity arrangement broadens significantly the existence range and allows for waveforms that, such as the one that appears here on the right, that otherwise do not exist in single cavities. So once we learn about how to control these microcombs, we went ahead and optimized the structure so that it could generate a microcomb with very high conversion efficiency, but also with more or less even distribution of power among lines. So what you see is the end result with about 24 lines that are generated with more than minus 20 dBm power, even though the photonic molecule is just pumped with 2.5 milliwatt of power. We believe that this combination of low pump power, high conversion efficiency, and even power distribution is really unprecedented in the field of integrated microcombs, and is a significant step towards realizing heterogeneous integration with lasers and opens new opportunities in coherent optical communications, where having more or less an even power distribution among lines is really crucial. So let me just go to the last part of my talk. And now I just would like to give a brief introduction to the field of coherent optical communications. Here, the idea of using microcombs is that they can be used as a multi-wavelength light source on which to encode data in the context of wavelength division multiplexing. So then the microcomb could essentially replace tens of individually tunable lasers. And there are really good reasons why you want to do that. First, with a microcomb or with a frequency comb for that matter, it's much easier to match the WDM grid. Essentially, you just need to dial the two frequencies corresponding to the 2 degrees of freedom of the comb, and then you will be able to hit the target channel wavelength. In turn, essentially, this avoids multiple temperature controllers, leading to potential savings in power consumption. In addition, the other thing that is very interesting with frequency combs is that the enhanced line spacing stability can be used to pack more densely the WDM channels, leading to higher spectral efficiency. And the other possibility is that the line spacing stability can be used to compensate for nonlinear impairments that accumulate upon propagation in the fiber channel. The other interesting bit that we used not long ago is the fact that frequency comb has very broadband phase coherence. So this means that if you look carefully at each line in the comb, the line width is not zero. It has a certain line width that arises due to phase noise. But this phase noise is correlated among different frequency channels. Okay. So then, in principle, in coherent optical communications, you could measure the phase noise on a single channel and use that information to compensate for the phase noise in neighboring channels. So this leads to a dramatic simplification of the DSP algorithms that are used in coherent communications. But this comes at the fact that you need to this comes at the expense that you need to measure simultaneously multiple frequency channels. So, in other words, this is actually a novel way of realizing wavelength division multiplexing, and is enabled by the fact that you have a phase coherent light source, and this will be totally impossible to do with an array of individually tunable lasers. Now, there's stuff, of course, that you won't be able to do with a comb. For example, switching on and off individual channels. So this has important implications for certain optical networking architectures. And also the fact that you have a single laser lighting simultaneously multiple channels introduces higher requirements in terms of reliability. So because if one laser fails, then the whole WDM stream fails. Unlike if one laser fails in a standard individually addressable WDM system with multiple channels, where you just need to replace a single laser. So of course, the challenge with using laser frequency combs for optical communications is that the available power then is divided among multiple lines. So this results in typically lower power than what you would get if you were using multiple individual lasers. So this means at the end of the day that the channels must be pre-amplified, and that results in a degraded optical signal-to-noise ratio per channel. But we did the analysis of this scenario where you have a limited OSNR at the transmitter. What would be the penalty of that you would get at the receiver? And we found out that if you tell me what is the OSNR at your receiver, just add 13 dB to it at the transmitter, and then you will be able to ignore the penalties associated with the fact that you have a non-infinity OSNR signal at the transmitter. So this is quite cool. For example, if you want to encode polarization multiplex 64 QAM at 25 gigabaud, standard information theory tells you that you need around 23 dB of OSNR per line. Just add 13 dB to it, and if you have 36 dB of OSNR at your light source, that's not infinity, just 36 dB, you will be able to run your system with essentially ignoring the penalties associated with a limited OSNR at the transmitter side. This, of course, is an oversimplified picture that does not include issues regarding line width or limited number of bits at the transmitter as the receiver. But the bottom line is that microcombs can actually offer the performance that is required to enable multi-terabit per second coherent communication systems in the context of WDM. So one very impressive recent experiment is the one reported by our colleagues at the KIT and EPFL in 2017, where they demonstrated 50 terabit per second using two interleaf soliton microcombs. So they engineered the dispersion of the waveguides such that they could hit both the C and L bands that are used for coherent optical communications. So they had close to 100 lines that were pumped with a single laser with 1 watt of power, but they had enough signal-to-noise ratio to encode high-speed 16 QAM and attain an aggregate data rate close to 50 terabit per second. That was very, very impressive, first of the kind demonstration. We did another set of experiments in collaboration with Andy Weiner at Purdue and Peter Andrexson at Chalmers using modulo dark pulse Kirkcombs. So what we demonstrated here was that the OSNR per line was actually sufficient to encode very complex modulation formats, in particular PM64 QAM, in all channels that were used for the comb. So that typically this sort of higher order modulation formats require much higher optical signal-to-noise ratio. The interesting bit here was that this dark pulse Kirkcomb was pumped just with 100 milliwatts of power, and yet we managed to get overall PM64 QAM on all channels at high speed, leading to an aggregate bandwidth of 4 terabit per second. So I just would like to finalize this section by putting things into context and addressing the question of how much better could we do using a state-of-the-art 10 million Qs dispersion engineered silicon nitride microresonator with regards to the amount of power that we can get for a given pump power. So I'm assuming here a constant pump power, just 100 milliwatt, and a microcavity that is engineered with either normal or anomalous dispersion. So I also assume that the power is going to be equalized to the weakest line. So if there is some homogeneity in the spectrum, this is going to be taken into account. And I'm putting essentially myself into a very worst cases scenario. So what we found was that these dark pulse Kirkcombs could achieve a performance in terms of power per line that is comparable to state-of-the-art electro-optic frequency combs arranged with discrete components. So the key difference is that with microcombs, one actually avoids completely the use of an external radio frequency signal and high power amplifiers. resulting in a very efficient way for generating a comb on chip. So now that we know that the power per line and the efficiency that can be obtained with the state-of-the-art silicon nitride microcombs is sufficient actually to encode advanced modulation formats operating at high speed, I think, in my opinion, the next frontier in this field is investigating what is the line space instability, how does it compare to state-of-the-art RF oscillators, what is the phase coherence, and whether we can utilize these properties for developing new concepts in WDM coherent communications that go simply just using the comb as a replacement of a bunch of different lasers. So this just brings me to the conclusions. So I think if there are just 3 messages that you can or won't remember from this talk, please let them be these ones. So the enabling aspect of microcombs is really the combination of large line spacing with the possibility of realizing on-chip integration. This could really enable a 3rd generation of frequency comb technology for precision frequency synthesis and metrology. So these dark pulse Kerr combs are a special class of solitary waves that exist in microresonators that have normal dispersion. They have been less investigated compared to their soliton counterparts, but they show really cool physics and they display very high power conversion efficiency, which makes them particularly useful for coherent optical communications. So the problem with dark pulse Kerr combs so far has been their control, which required this fortuitous interaction between 2 transverse modes in the cavity. So what we have shown is that we can engineer this interaction with a suitable arrangement of 2 linearly coupled cavities. This results into a photonic molecule system where the longitudinal mode spectrum results in comb states that do not exist otherwise in single cavity arrangements. And these cavities can be engineered to produce extremely flat and power efficient microcombs that operate at ultra low pump powers. So that's everything for today from my side. So thank you very much for your attention. I'm looking forward to your questions.
Thank you very much, Victor. So any questions to Victor, please? So we have like 5 minutes for discussion.
Thank you very much, Victor. I have a question. Do you hear me?
Yes, I do.
Yeah, thank you. So I have seen your stability chart for the dark pulses as a function of a square of normalized pump and normalized tuning. And basically, my question is, how did you obtain this phase diagram?
Yeah, this is very extensive work. So essentially, I went very quickly here, but what you do here is for every single point in the diagram, yep, you launch a simulation considering the linear interaction between the 2 modes.
And so you analyze the. So it's like Newton-Raphson method, or you're trying to soft excitate the pulse in the cavity.
No, you start with a CW with noise, and then you end up. What we do is it's an Aikida map where we solve where we solve 2 linearly coupled nonlinear Schrödinger equation, and we solve it in a round-trip by round-trip manner.
And why don't you use LLE?
Sorry?
Why don't you use Lefebvre formalism?
In principle, you could, but one thing that we like about the Aikida map is, well, we like 2 things. One, that it allows us to explore a broader range in coupling coefficients between the bus waveguide and the arrangement of ring resonators. And the other thing is that it allows us to introduce noise in a round-trip by round-trip manner. So that helps us in quantifying better the signal-to-noise ratio and phase coherence of the steady-state waveforms.
And does it help a lot in comparison to LLE?
Sorry?
Does it help a lot, this possibility to introduce phase noise to the field envelope on each round trip in comparison to LLE?
I think for the phase noise and for exploring a broader range of coupling coefficients, it does. I don't know whether it would give you substantially different maps when you look at something like we have here in terms of the existence range for different pump hours and normalize the tuning. But we started for the reasons that I mentioned with the Aikida map, and then it was just natural for us to extend this into the two modes and explore the arrangement of linear coupled cavities.
Okay, thank you. And one more question. So this stability chart was obtained for a particular dispersion profile, isn't it?
Yes.
And if you change, for example, coupling between two modes, I mean, if you change the strength of avoided mode crossing, this map will change significantly or not?
Yes, they will change.
Okay, thank you so much.
Mm-hmm.
Okay, thank you for your question.
I have a question.
Yes, please, Paul.
Yeah, as a follow-up to that last one, how do you tune the coupling between the rings? Is that what this heater is below? On your last slide, you had a drawing of that.
Yeah, here you have two handles here. So one is with the gap distance between the main and the auxiliary cavities that will change the coupling coefficient, and then with the heater you control the longitudinal mode spectrum of the auxiliary cavity. So then you essentially control the location where the split resonance takes place, and also to a large extent the magnitude of the strength of the coupling.
Okay, thank you.
Thank you very much for the questions. And if you have one more very short question, then please go ahead with a short question. If not, then thank you very much again, Victor, for your very good presentation. And let's move on to the next talk from Professor Pascual Muñoz. And the title of the talk is Silicon Nitride Photonics Ecosystem. Yes, Pascual, yeah, please try to
Thank you.
share your slides.
Thank you. Let me see. This kind of things always give troubles when you are live. So let me see if I can share. I'm gonna put presenter mode, and I'd appreciate if you tell me that you are seeing my full screen. So I assume yes, you see the introductory full presenter screen?
Not yet.
Not yet. So kind of other than Victor, maybe. Let me see. Okay. What about now?
Now it's good. Now it's in the presenter mode.
Now it's in presenter mode. Fantastic. Thank you very much. Okay. So thank you, and thanks for the invitation to give this talk in the Microcomb ITN webinar series. My name is Pascual Muñoz. I'm a professor at the Universitat Politècnica de València. And today I will give an overview of the silicon nitride photonics ecosystem, which are the technologies that are available. And I will conclude also discussing what I see as challenges and opportunities in this ecosystem. So, okay, now, so I'm on slide 2 myself. Please, can you confirm that you see that? I assume.
Yes, looks great, Pascual.
Okay, fantastic. Thank you. So now I'm not asking anymore then. So I have sectioned my presentation in a very short introduction about me and my group, and then I will dive into the main parts of the presentation, which is an introduction to the photonic integration ecosystem. As Victor, I decided to step back a little bit, since we have let's say young researchers in the audience. I would like to show how we reach the present state of photonic integration. So that is the first part of my presentation. Some of you have already seen it somewhere else. And then on the second part, as main dish here, what I will do is discuss about the silicon nitride technology and the open foundry efforts that are available, and I try to cover from the visible to the mid-infrared wavelength range. And finally, as announced before, I will just conclude just presenting 3 challenges and opportunities related to the ecosystem. So just very briefly about myself. Up to my postdoc, I researched on the different generic integration technologies in phosphide, silicon on insulator, and silicon nitride. And then with my own group and collaborating with different universities and companies around Europe, we saw a business opportunity and we spin off a fabless company doing business on peak prototyping, which is VLC Photonics. After some years, I became full professor at Politècnica de València, and very recently I'm trying to let's say complement our fabless skills with some sort of fab or foundry, and we are reading up a microfabrication R&D and pilot line in Valencia. So this is thanks, of course, to the efforts of all the group, not only the current members that you can see here. So there is Professor Pastor, which is listening, and also Roel van der Zoon, which is the ESR in Microcomb, but all the other postdoc and PhD students and clean room personnel as well. And past members, I am really very thankful to the past members of my group, which I list here, and there are a few more. But I am very proud of them because they show that we could take something from the university and turn it into an actual company. So nowadays we are working on the photonics research labs as a group, and that laboratory it's an optical telecom lab that has equipment for in very short digital up to 40 gigabit per second and RF analog 50 gigahertz that we're going to be upgrading this soon. And as I said before, we are now starting up or making readily available a clean room that was formerly a solar cell manufacturing facility, and now we are opening it up to groups in photonics, electronics, and chemistry in our campus. So that is a short presentation about us, and then let me go to describe the ecosystem of photonic integration. So I think that Victor portrayed very well what has happened with frequency comms. And he showed a picture with a big, bulky setup, and then how this evolved into an integrated equipment, and now how it is going to an integrated microresonator. So this is the same thing that happened in photonic integration. So you may recognize an optical table, which typically is 2 by 1 meter square size. And this is kind of things that we do in a photonics lab with discrete components, fiber splicing and such. If we use lenses and polarizers and such kind of things, it gets even more complicated. And this is something that, of course, you cannot carry on your backpack, right? So it is nothing but portable. Integrated photonics is nothing new. It was already announced in a very old paper. This is from 1969 by Stuart Miller. And he envisioned the integrated photonics as a miniature form of everything that you saw in the previous slide. So, of course, for technical reasons, so it could be isolated from the different effects happening around, but also because it could be economically sound to manufacture in mass this kind of technology. This was done already by electronics, so photonics is coming a little bit after, but In electronics, what we saw, and if you want to have further details, you can just go to my YouTube channel and see this video. What we saw is that companies did everything themselves in-house. That is called integrated device manufacturer. So the manufacturing tools, the software tools, the application, for a given market, everything from bottom up. And a long time in electronics, different parts of these activities were disaggregated in different companies, and it gave the possibility to companies that didn't have any fabrication facility to use the manufacturing tools and the software tools and the existing manufacturing processes to do their own products. And the right-hand side graph is an evidence of how the evolution of fabless company in electronic integrated circuits I'm talking about now has been growing in market share as compared to the always present IDMs. But at least fabless ecosystem seems to be something that is let's say a good way of doing for electronics. As I said, in photonics we are lagging a little bit behind. In photonics, what we had is, since this seminal paper by Miller, what we had was the evolution of optical telecommunications and vertically integrated companies doing very specific components, such as AWGs, splitters, BOAs, a laser, a detector, a modulator. But then in the 2000s, we have the telecom bubble burst, and most of these things disappeared, but some of them were reconverted into generic technologies that I will describe in short, and that gave rise to the appearance of fabless companies in photonic integration. So currently we have a lot of fabless companies that are using the fabrication capabilities of many other to do their products. So, and that was possible because there was a change in the way of doing photonic integrated circuits. Formerly, and I like to portray this toy analogy. I know that it creates divided reactions. Either you like it or you don't like it at all. Either you use a dedicated process, which allows you to do only a very specific thing, or you use a generic process like the toy Lego that we all may know, in which it depends on how you combine the different pieces, you end up with a different toy, in our case, a different application. So this generic way of doing photonic integration was developed, has been developed in the last 15 years, I would say. And then now we have technologies that have like the very basic building blocks, like the waveguides, the optical phase shifter, the optical amplifier, and the polarization converter. That's how we call fundamental functions. You can combine them to make a slightly more advanced component, which is a building block, for instance, an MMI coupler, a ring resonator, for instance. And then if you combine several of those, you could do a composite building block. In this case, we have here a laser with a gain section and 2 DVR mirrors and a phase shifting section. And overall, this is a photonic integrated circuit as we know it today. So a circuit that has a lot of functions on it, and that performs far more advanced functions than the ones in the early 2000s. This, of course, has been also possible by mirroring not only the technical part of the history from microelectronics, but also sort of the organizational part and the business part. This has been also possible because some of the foundries that developed these photonic generic integration technologies opened up, and then they use multi-project wafers. So instead of a user paying a full wafer, the design reticle is divided among different users, and you just pay for the area that you are using. In such a way, you have a cost-effective access to technology, and you don't need to develop your own technology. There are technologies that you can use to make your proof of concept devices, and later on, maybe you need to make an adaptation when you do dedicated runs. And finally, I would also like to give an overview of, and there may be more, okay? This slide could be growing probably forever, will be growing probably forever. But I just highlight the, let's say, the first pioneers in generic photonic integration technologies, and I like to put them in context of the applications. As we are very familiar with, applications depend on wavelength. For instance, tele and datacom are in the near infrared because the optical fibers are transparent in the near infrared. And then biophotonics is usually done in the visible because the visible radiation is not ionizing. Does not ionize living tissues. And sensing is usually done in the long near infrared, mid infrared, because the molecules have vibrations with fingerprint in that region. So application is dependent on wavelength. And then if you want to put that on a photonic chip, you can use different materials. As I said, I am only referring here to generic integration technologies, so 3-5 semiconductors that typically cover this range. Then you have silicon insulator that typically covers more or less the same range, a little bit less, should we say. And then we have the one that is like the star of the talk today, which is silicon nitride technologies, which up to now has been used in combination with silicon dioxide, and thus it covers from visible wavelengths to 2.5, 3.7 microns, depending on the quality of the oxide. Okay, so this is the first part of the presentation, photonic integration ecosystems. And now let me talk specifically about silicon nitride technology and the open foundry efforts. So having silicon, why would we use silicon nitride? This is, of course, a table, and you can take it with a pinch of salt because, so broad or generic comparisons can be unfair in some specific cases. But basically, we would advocate for silicon nitride for the reasons that are not here in red. Okay, because it has low scattering loss, low birefringence if you engineer well the waveguide cross-section. It can cover a wide wavelength range. It is a material which is CMOS compatible. It has been there as a functional material or helper material in CMOS electronics since the very beginning, I would say. And for the nonlinear processes where you may require high input power, you don't want to lose power in other mechanisms as to photon absorption in the silica, it is as well advantageous. Of course, it has its own disadvantage, which is lower integration density because of the low refractive index contrast. But anyway, for passive circuitry, I will be putting some takeaway messages in the slides as this. So for passive circuitry and a broad range of wavelength, silicon nitride is definitely advantageous. If you want, this is perhaps for the students, if you want to learn a little bit about the historical developments of silicon nitride, you could resort to this reference of us. If you want to know the current state of silicon nitride foundries that provide open access, you could read this paper. I will discuss a bit of it in the next slide. So I just give this for completeness. So in terms of foundries that develop generic integration technologies and then have an open access process in a multi-project wafer scheme, as mentioned at the end of the last section, we have Lyonix, we have Ligentech, which is the spin-off from EPFL, as we all may know. We have CNM, the National Center for Microelectronics in Barcelona in Spain, and we have IMEC. And they have different kind of processes with PDKs, process design kits, so libraries that you can use with the software to design for these technologies for different software providers. And then within these PDKs, and probably this table needs adaptation, even if it is only 1 year old, you have different building blocks, so you would not need to redesign from scratch every component that you need on your chip. You will have available things like directional couplers, MMI, export size converters, and so on and so forth. And it is also important to understand when you work on the ecosystem, the time scale of things happening. So that is why in the particular case of the silicon nitride foundries, I would say that from the time that you deliver your design and you get your chips back, it can take like 3 or 4 months. So that is something to consider when you're planning your research. There is another table in that paper where you can get technology details, in which is the wavelength range of operation of a given technology, which are the dimensions of the different parts of the layers in the technology, like the substrate, the guiding nitride layer, and the cladding, and which is the typical cross-section with the given features that the different groups and the companies have reported. I allow myself to highlight today here 2 of what we call the thick silicon nitride technologies, because these are totally related to the topic of the ITN Microcomb, because these are the ones that are amenable to exploit the nonlinear optics with a cross-section that exceeds low loss. And in the open foundry players, we have this technology. This technology is provided by Ligentech and provided by Lyonix with different performance if you are interested in them. As examples of nonlinear chips, I would like to quote from the open foundry part, I would like to quote EPFL and Ligentech works that you will be very familiar with. So for comb generation and different applications like biomedical imaging and very recently microwave photonics filters. And of course, you already saw the presentation by my colleague Victor Torres from Chalmers on comb generation on their own proprietary silicon nitride platform. What I would like to highlight is that these platforms have the ingredients to perform the nonlinear generation, but of course they can also be used to complement this nonlinear generation with linear operations. And for those linear operations, it's usually interesting to have a kind of tuner mechanism. Both kind of platforms have thermal tuners. And as I say, they are amenable for something a little bit more complex, if it can be, because nonlinear generation, at least for me, that I'm a linear guy, it's very complex. So I would also like to describe in the ecosystem the technologies that we have been working with the National Center for Microelectronics, because I believe they are very relevant. They start in the visible, go to the near infrared, and we are currently working on a mid-infrared technology. All of them are based on LPCVD silicon nitride of different thickness. Thickness in visible is because we use a multi-mode waveguide. Thickness in the near infrared is a compromise on integration density and propagation loss. And then for the mid-infrared membrane technology, I will give some hints later. But this is the portfolio that we have been developing from research groups and companies in Spain in National Center of Microelectronics. I will go for the visible very briefly, and I will quote 2 examples. So the example on the left is a bimodal waveguide. It's a sort of Mach-Zehnder interferometer, if you want to look at it that way, but in a straight line in which this first section has one single mode and this one has 2 modes. And then you create an opening here that you expose to the outer media to feel what is outside. I will put this video that is courtesy of my colleague, Professor Laura Lechuga from ICN2. So in this video, you see that this part, that this edge is functionalized, so that some analyte can bind to the chemistry that is on top of the waveguide. And depending on the amount of analyte that is binding, you will sense a different interference in a detector which is placed after the waveguide. It is a detector with 2 areas, and you just make a comparison of the intensity in the upper part and the bottom part, so as to infer how much analyte has been attached to your waveguide. I would also like to mention in these dates, I believe it's important that Professor Lechuga is leading one of the ACE 2020 projects on the COVID-19 call. Then there is another application with from Dr. Sein from Norway, in which they use this silicon nitride to provide ultra high resolution fluorescence microscopy. I have a little idea of what is going on here, but I just quote it because I believe it's relevant to know that not all photonic chips are telecom. So in the visible, they are mostly for biophotonics. Then in the near infrared, CNN has a platform that was developed by VLC Photonics, as I mentioned before, and it has kind of cross-section in which you can have different types of waveguides, thermo-optical tuners, and selective area trenching. It can be accessed in a multi-project wafer fashion. So if you are interested, you can write to this address here. I just wanted to quote it. And within that technology, and this is a result from our research group, from one of the PhD students, which is actually an industrial doctorate at VLC. What we have demonstrated is a reconfigurable spectrometer. This is somehow linked to the work that we will be doing in the ITN Microcomb, and I will present later. So it is a device in which it is sort of a WDM filter, if you want to link it to what Victor presented in the last part of his talk, in which you can actually reshape the fast band, and we have made a lot of experimental demonstrations with the same chip, 11 shapes, 20 dB rejection. We did it at the optical telecom C band, and since we're using a silicon nitride platform, which is also transparent in the lower part of the near infrared, we also did it at 1310. So this is our first proof of concept of a WDM multiplexer that could be reconfigured, or if you look at it at the broader view, it could be a reconfigurable spectrometer. And it has all the ingredients that we will be using in the ITN. It has a spectral shape, and it has a reconfiguration with Mach cylinders and thermal tuners. So last part of this section on technologies is to wonder how to go to the mid-infrared, because as I said before, mid-infrared is of interest for many sensing applications. But so far, the attempts that we've seen in the literature and in the market are done with combination of germanium on silicon by Cialetti, and also by ORC Southampton, if I am not mistaken. So we wonder why could not we use silicon nitride? And if we resort to what the literature says about the properties of the materials, the only thing that prevents using the current silicon nitride-based platforms for the mid-infrared is the silicon dioxide, which is around the silicon nitride. It's strongly absorbing close to 4 microns. So we should avoid using silicon dioxide. And we have been working for a while already with CNM on a technology to create a silicon nitride membrane. In fact, we just finished a design of experiments in which we had a full wafer with test structures, and those test structures are scaled for 3 different wavelength ranges within the same wafer. So within the same wafer, with the same silicon nitride thickness, with the same lateral edge of silicon nitride, we're going to be having chips that work, hopefully, in between 1-2 microns, in between 2-3 microns, and in between 3-4 microns. They have been designed to operate monomode in that wavelength range. So these activities, of course, pause as most of the things in the world today. And what we need to do when we are able to come back to the clean room in CNM is to improve some of the processes. We of course, are in an early stage and are having some issues with the processes. We cannot admit it, and we will start doing OFDR-based characterization at UPV with some of the first chips. I will discuss about this technique in the next part of the talk. So last part then on silicon nitride technologies. What are we bringing to Microcomb? What is our group bringing to Microcomb? We are bringing a linear processor so as to help shaping combs. This is something that was underlining on underlying on during the presentation by Victor. But our aim is to complete some of the platforms with linear processors. So we have the comb generator, and within the same chip, something that can split the comb, process the amplitude and the phase of the comb, and then combine it back again. It seems like a very kind of a straightforward problem, but I can tell you from our past experience on the reconfigurable spectrometer that there are many issues, technical or engineering issues on this that are not trivial. For instance, which is the state of your machine when you start? How can you know it? How can you be sure that you're setting the amplitude on the phase that you require? So this is not rocket science, but it is not naive either. And I think that we're going to be adding quite a lot of value to the nonlinear part of the ITN Microcomb. The ESR Roel van der Zon is working on the different areas. So at the moment, he just started working with the PDK from Ligentech, but of course, everything he's doing can be adapted to other PDKs by Chalmers or others immediately, because it entails different abstraction levels. So first abstraction level is to make an analysis of the technology, a cross-section analysis that allows us to understand how the waveguide works in terms of model and dispersion, and then to design the different building blocks that are required for the spectral processor. This, of course, has links to a layout library that is used afterwards, because all the results from this building block design on the technology can be back annotated to an matrix-based library of compact models. So upon system specifications, for instance, I can envision some of the applications by Chalmers will post some specifications. We will put these specifications into our models at a circuit level. And then when we are happy with the circuit level, we will be able to use the mass layout library to follow with photonic fabrication. We have done already, Roel has done already the things that are in red. And then next pending actions are marked in green, I meant, and then next pending actions are marked in red. So this brings me to the last part of the talk: challenges and opportunities. Ignore this. This is probably from another talk. So the first challenge and opportunity is, how do we know what is happening inside peaks? So the peaks are becoming very complex things. It is no longer a piece of waveguide. It is not only a single ring resonator. It is something that has a lot of structures inside, and you would like to be able to explore them piecewise, even when they are all connected in the full final circuit. So, I was saying that with the combination of these two things, you can have an interferogram that has both the amplitude information and the phase information of your device under test. And then you get that spectrum, amplitude and phase. You make an inverse Fourier transform, and you get the temporal response. For instance, in a ring resonator, and we will see an example in short, you would get the different contributions in time of the different recirculations in the ring resonation with resonator with amplitude and phase. This is one example from us. This is a very long ring resonator with an MMI as coupler, very simple. And this technique allowed us to see the different recirculation peaks in time. So we converted the space to time. And then you can have the first T peak, the second, the third, fourth, etc. And you can also see the TM mode. And from them, by relating the different peaks, you can derive the dispersion of the waveguides that are forming your ring resonator. We did also this in cooperation with Chalmers. They did a couple of micro rings, and then we used this technique to analyze them. And we got this kind of temporal traces, similar to the ones that I showed before. And then what we did was to compare the different pulses. So this is a superposition of the first pulses and then a superposition of the last pulses. So you can see that they are broadening because of dispersion. You can then make a Fourier transform and compare the phases of this, and you can estimate the dispersion. So you can get the dispersion parameter. From this decaying, you can also fit the coupling coefficient and the intracavity losses, of course, the group index because of the peak separation. And not shown here, but you can also see spurious things that happen on your chip, like unwanted reflections on the facets. The facet that is natural, but if something has a sort of a spurious reflection inside the chip because of a bad design or an unexpected thing or something that you did not consider, you will be seeing it on the temporal traces. So it is a challenge for us, but we are trying to promote this to incorporate everything on chip, because as far as I've shown, the device under test was on a chip and everything else, the Maxinder interferometers, were out of the chip. And that creates some sort of uncertainties that we have solved only, let's say, by bringing it into chip. But I would add only by bringing it into chip and adding some sort of a little bit of design. So we have the device under test, in this case was an AWG here, and we have this Mach sender going to this port, and then this is the device under test Mach sender, and this is the triggering Mach sender on this other side. And we have been able, as I mentioned, to see the different contributions of the different waveguides that have different lengths, and that is why they appear at different positions or spatial positions or times in our measurement traces. So we are able to isolate the different paths to get the amplitude and phase of the different paths, and this is very important in interferometric devices. Now that we have this, what we want to do is to bring this together with a wafer scale photonic tester. And this is again, and I come back to what I said at the very beginning of my talk, to mirror what CMOS electronics has done. CMOS processes entail a lot of process steps, which are complex and of course are costly in time and money. And CMOS electronics set test structures and test strategies to discard wafers that were underperforming at the very beginning of the steps or after each step. So the process was not completed for all the wafers, only for the ones that were performing well. And then this is not present in photonics. And this is going to be getting even worse when we try to hybridize the silicon nitride, for instance, with 3.5s, as Victor mentioned in his talk, and I will be discussing in the next challenge. So what we are proposing and working on is to bring these advanced photonic test structures to the wafers, so we can validate from a photonic perspective, not from a structural perspective or material perspective, the fabrication. And then we either give go or no go decisions for the next fabrication step. Then challenge 2 is hybrid photonic integration. So far, what I showed in the first part of my talk was that the different foundries have available in an open fashion processes that are on a monolithic platform. 3.5 semiconductors, silicon nitride photonics, or silicon on insulator photonics. We are starting to see since a few years ago the combination of silicon on insulator and silicon nitride as well. And we're seeing a lot of attention being paid on bringing the actives, the 3.5s, to the silicon nitride, and many market reports support this. So we believe this is point in which the silicon nitride foundries have an advantage because they can guide light from visible to the mid-infrared. So that means that you can have a single, let's say, platform for the passives and then combine with the different actives at the different wavelengths, depending, for instance, on the band gap of the semiconductor that you use to build your actives. Since you are doing this in such a broad, wide wavelength range, that means that it probably does not pay off to have a dedicated process to hybridize for a given wavelength, and then another different process to hybridize for another different wavelength. So we believe that there is a very nice technique, which is microtransfer printing, that has been demonstrated in photonics by our colleagues in Ghent, and in our case, in our pilot line, we are incorporating one of these tools in 2021. We believe this is the way to go, and with the numbers that that Victor showed, 2.5 milliwatts for pumping with hybrid integration, this is something that probably is going to be a very nice match with the Microcomb generation on chip. And then the number 3, this is a mistake, sorry. Challenge number 3 for us is chips are getting more and more complex. This is another example from colleagues at Photonics Research Lab, in which they have a very complex chip with a lot of reconfiguration elements. And these reconfiguration elements so far in silicon nitride are based on thermo-optic phase tuners. And it is quite straightforward, I would say, to design them if you just want to make a proof of concept. But what if you want to increase the integration density first, make them efficient second, and then make them durable? So that is another thing or another topic in which this student of my group is working. Is studying the different cross sections that we could create with available processes and the different tuner materials that are available in any foundry, I would say. So selective area trenching, undercuts, materials for the heater lines such as gold, aluminum, polysilicon, and then cross sections that incorporate thermal shunts like the cladding with alternative materials other than silicon dioxide, metal vias, etc. But the goal is to understand and optimize the figures of merit: power consumption, crosstalk speed, footprint, and durability. Sometimes these 2 guys are forgotten by most of the people that is making a proof of concept. And we believe if high density integration and reconfiguration with very simple technology, that is a thermal tuner, is going to happen in silicon nitride, footprint and durability is something to look at. Well, and that was the talk. I will go to the conclusions. So in the first part, you've seen, and most for the novel part of the audience, what is generic photonic integration and which are the technologies available to which you can access through MPW runs. And then you can do that in manufacturing facilities, by the way, perhaps I didn't mention, that are the same in which you could scale up for mass manufacturing. And it is comprised of several mature platforms: indium phosphide, silicon insulator, and silicon nitride. With silicon nitride photonic technologies, we've seen that it has several actors in the ecosystem with complementary technological capabilities, and that it covers currently visible and near infrared, and is sought to cover as well the mid infrared. As a takeaway message, as I said before, the silicon nitride provides a straightforward way of combining nonlinear and linear photonic, reconfigurable photonic on a chip. And in the last part, I just highlighted these 3 challenges and opportunities, which is having means of looking inside your chips at wafer scale. Perhaps on a research project, this may not seem important, but if you get used to use this look inside technique from research later on, when everything is scaled up, it will be very natural. The second challenge is related to the fact that the silicon nitride photonics is a passive technology, and that we will require to hybridize with 3-5 materials in cooperation with different 3-5 fabs. And since you don't want to do and to reinvent the hybridization for every different application, microtransfer printing seems a very nice candidate. And then the last challenge is, okay, reconfigurable integrated photonics on silicon nitride. Thermal tuners are available, but how we can improve them in such a way that we can put more, they are more efficient, and they are reliable and durable. And that is it from my side. So I will be very glad to take your questions. Thank you very much.
Thank you very much, Pascual. for a very nice presentation. And questions, please, to Pascual.
Hello, Pascual. Thank you very much for your nice presentation. So actually, I am wondering, because in optical frequency domain reflectometry, the precise calibrations of laser is very important. So how do you calibrate your laser? And my another question is, what is actually this interferogram needs to be discretized in frequency, precise frequency interval, in order to avoid this non-linear sweeping of laser. So what is the resolutions of your discretizations of your interferogram in terms of frequency? So my two questions is, how do you calibrate, and what is the resolutions of your discretizations of your
okay. Now I get the second. Thank you for your questions. Okay, the laser calibration, probably you refer to the fact that tunable lasers scan in wavelength that probably they do not scan in a continuous wave, right? So it is not a linear scan. I mean, ideally it's linear, but not in practice.
Yeah, that's my concern. Yeah.
Okay, perfect. So that is why in parallel to the Mach-Zehnder that has the device under test, you have a triggering Mach-Zehnder. So a Mach-Zehnder that keeps track up, down, up, down, up, down, an interferogram, an additional interferogram that you can use to sample the device under test interferogram. So that way you correct the imperfect tuning of the laser, and that is your laser calibration. I guess that answers your question. Okay, and then in terms of resolution, that is limited to your tunable laser. The ones that we are using in the lab are, of course, high-end tunable lasers with 1 picometer resolution. But I would say that you can design your OFDR engine, so the different path lengths in the Mach-Zehnders virtually to use any tunable laser. And of course, yeah, there is a compromise on the tuning range, so as the minimal space resolution that you get, and there is a compromise on the laser resolution, as you quote, and on all the space that you can see, basically.
Okay, thank you very much.
You're welcome.
Okay, do we have more questions to Pascual? Yeah. Okay. Well, it doesn't look like we have more questions. So let's thank you again, Victor and Pascual, for excellent presentations, and hope to see you again soon at the beginning of June at our next appointment. Okay, thank you very much, everybody. Bye-bye.